Okay, so first off, last class, when we talked about the project, I said I would take a week to figure out what to do with it. I decided to take the path of least resistance, which is to just allow an open project. So you can do a project on anything. It does have to relate to the content of the course. So I'm looking for a project that's either going to be about cryptography beyond 6110. So not like about a block cipher or just digital signature or something that you're going to see in that course. Something more advanced than that, that's okay. Or it can be about a network protocol. All right. You can do one of two things. You can either do...
Can it be both?
Sure. Yeah. Of course. Yeah. You can either do a novel research topic. So that's something that like nobody's done before. This is appropriate, especially anyone can do it, but if you're in a thesis-based program, master's, PhD, that type of thing, you're probably wanting to get an academic paper or a chapter for your thesis. And so doing a class project that could serve as a chapter of your thesis is something that you should always try and do because you have to do the work anyways. And the other option you can do is what I call a systemization of knowledge. It's like a survey paper kind of. You're going to read other people's research and report it. But I have some specific guidelines about what makes it different than a survey, which I'll mention now. Okay, so when I think of a survey, I think I go out and find 5 papers. And when I write the survey, I'm going to tell you what those 5 papers say. Okay, so I read this paper and this is what it says. I read this paper and this is what it says. I don't want that. What I would rather have is you explain a topic to me. So think about it like I hired you to write a chapter of a textbook on whatever the topic is that you chose. Okay, you probably never picked up a textbook in your life and it's like, there was this guy in 1985 that wrote this paper and this is what it said, okay? No one cares, right? We just care about what the actual topic is itself, okay? So your job is to read the papers, understand them, process them, and then tell me something about the topic itself, all right? So approach it more like you're writing a paper for all your friends to read to understand what this particular topic is that you chose. Another thing to help you is pretend that I've already read all the papers. So you have 5 papers, you're basing your project on those. Pretend I've already read them. So I don't need to be told what they say. I know what they say. Tell me, what's interesting about them or how they relate to each other. Explain the topic that they're about to me in your own words.
So, but like the way you cite a paper is the same way?
Say it louder, sorry.
The way you cite the papers is the same way?
Mm-hmm. Yeah, so the way you cite it, you still, whatever you say that you drew from somewhere else, you need to cite it, yeah? So there'll still be lots of sentences with a citation to the paper, but it's not like, you're not going out of your way to explain what the paper is. Another way of thinking of it is you're only pulling in what you need from that paper to explain the thing that you're explaining. You don't have to, let's say it starts talking about something else, right? If it's a survey, I have to talk about what else it talked about because I'm trying to summarize that paper. But if I'm just pulling that one piece in, that's all I need from that paper. Does that make sense? Okay. Okay. Now, okay, what are all these papers that I'm talking about that you talk about? So you're going to pick a research topic. That's fine. Then you have to learn about it. Right? I assume you don't know anything about it or you don't know enough about it to write a project. So that's the research aspect. So you're going to get that knowledge from somewhere else. Okay? Now, one place I'd like you to look is at other academic research papers. Okay? And see whether they cover that material. The way to find those is go to somewhere like scholar.google.com is probably your best. And then you can type it in. You can try asking ChatGPT. Papers are the kind of thing it hallucinates. So it's I don't know why, but for whatever reason, it tends to talk about papers that don't even exist. So you can try it, but whatever it's telling you, you should actually grab a copy of the paper and make sure it actually knows what it's talking about. You can do the opposite, though. You can find a paper, drag and drop it into ChatGPT and say, summarize this paper for me. Okay, now some topics are going to be so new that there's not academic papers on it yet. Academia tends to trail because there's a whole peer review process and things like that. So sometimes there's things that happened in the last 3 months. There's not going to be an academic paper on it. That's fine. Do that for your class project. I would like you to do that. I'd like to read things that are new. And in that case, you can rely on blog posts or technical things or code or whatever, wherever you're getting your information from, and that's fine. So there's not a requirement that you must use an academic paper. The requirement is sort of the opposite, which is if you choose a topic and there are academic papers on that topic, don't ignore them. Okay, do read those ones. Okay, so the only time I'll have a problem is if you're talking about something and I know for a fact there's a paper about that, but you're not even talking about that paper at all, or you don't even mention that it exists. Okay, other than that, you don't have to go out of your way to use papers. Secondly, you're starting with a topic. Okay, so whether you need to refer to one other paper in order to explain that topic, or 5 or 10, that depends on the topic, and it depends on what the other papers are talking about and how good they are at like giving you the knowledge that you need for your project. Okay, so there's no rule like you should go read 3 papers or you should go read 5 papers. Okay, you should pick a topic and you should read enough so that you can explain that topic to me in your project report. And wherever you get that information from, you're going to cite it. Okay, so there's not a set number of papers that you need to read. Another thing is when you read papers, keep in mind that the papers could be wrong. Okay, especially if you go on Google Scholar, it pulls in all sorts of papers that people write. Maybe it's a class project. You could take your class project, you could post it on a website like Archive, and now it's an academic paper and it gets referenced in by Google Scholar. Doesn't mean anything. It doesn't mean it's right. It doesn't mean it was peer reviewed. Doesn't mean you got a good mark or a bad mark. It's just anyone can put a paper on the internet. Okay, and so you can't trust every paper. So as you read it, I want you to think critically about it, and I want you to think that there is the potential that this paper is wrong. And so let's think about that as we read it itself, okay? Now, there are some indicators that a paper is good quality. So some things are, if you look and see where it was published, then you can have a conversation with ChatGPT, or you can go to conference rankings and things like that and try and figure out whether that's like a strong venue or not. You can look at the number of times the paper has been cited. Not 100% true, but usually, if it has 100 citations, it's probably a good paper. Okay, if it has no citations or low amount, it's not necessarily a bad paper. It just might, people haven't read it. It's too niche. It's too new. It takes a while for papers to build citations and things like that. But anyways, the main point is that you be skeptical as you read these papers. You don't just repeat it as if it's true just because you read it. Okay, topics. Let me jump to the last point. Okay, struggling with a paper project topic is normal. Okay, so that's like, I always think of it as like 25% of the work that you're going to do on this project will just be coming up with the project topic. Okay, so it's normal. You don't know what to do. You can do anything. You look at network protocols. There's 2,000 network protocols. What are you going to do your project on? Okay, that's normal, right? You want to do a good project. You're going to struggle trying to find something. Okay. So that's normal. Don't feel bad if you're struggling, but you got to push through and actually choose a project topic. One thing that you might do is you might take a look at what is the current research that's being published. So I listed the 4 major conferences, the big 4 security conferences. There's lots more in the world. And these tend to be, because this project is more crypto, there's actual crypto conferences as well. This is more security, but they do have crypto papers that are very applied, so they're appropriate for this class. But you can look through those, and each one of these publishes a couple hundred papers a year. Okay, so even if you just look at 2025, you probably have over 1,000 papers. And so you're not obviously going to read all of the papers, and this is just 4 conferences. But what you can do is look at titles of papers. Okay, so you can read 1,000 titles. It might take a bit of time, but you can do it. And then you can find the titles that are interesting, right? And then if it's an interesting title, A paper is going to have an abstract, which is a sort of one paragraph summary of what the paper is about. You might read a couple of those, and you might decide that some of them are interesting, and then you might go look at the papers themselves, drag into ChatGPT, ask it to summarize it, whatever you want to do, okay? So that's how you could narrow down. Now, that's not a project topic yet, but that is, I found something that I'm interested in. It's something I could see myself working on, for however long it takes to do one of these projects. And it's not going to be really grading to do that because, I don't care about that topic at all. It's a really boring topic. It's something that I picked, okay? And what you'll find in these major conferences, hopefully, is there's a whole wide variety of stuff, okay? And there's lots of stuff that's applicable to real life. They're not all theoretical papers. And hopefully you go through it and you find stuff that you're actually interested in. Another thing you can do is, I think I mentioned this last time, but think of this as something you can add to your CV. Okay? If you write a project, you could put the project title on your CV. I don't think any employer cares about what project you did. But if you do something with it that's interesting, maybe you get it published. That's something that people might care about. Let's say you write a bunch of code and then you have a GitHub link to that repository. You have a summary of the code. Then it's a real life thing that you can show someone and they can look at it and see what you did. So think about that too. It's not just about your mark in this course and just trying to get through the course. It's also a chance to set yourself up in the future, for a job or something like that. Question? Yeah.
If our project is really interesting, can we create a thesis based on this?
Sort of not really. So this is the way a thesis works. So a thesis is a separate program. So I assume that you're in the MEng program, or?
I'm on the thesis, but if I want to do a new thesis based on this, if it's interesting.
Yes, of course. Yeah. So whatever you do for the project, it's yours. So you can do what you want with it after this course is done. So you can expand it, make it a chapter of your thesis. You could try to expand it all the way to a thesis. That's between you and your supervisor. Yeah, what you want to do with it. Yes. And you should be thinking along those lines because you have to do something for the project anyways, right? Why waste all this time for something you're just going to throw away when the course is done if you could leverage it for something else?
If my thesis doesn't have the exact competencies on this project, can you also be part of the process or no?
I didn't quite understand what you mean, but.
If I want to do my thesis based on this project,
Yeah.
my thesis supervisor doesn't have the specific knowledge based on what I'm doing here. Can you be part of the thesis as a helper or no?
Yes, yeah. So it's subject. Anyone can help you with anything. So you can have co-authors on the chapters that become papers. You can have supervisors. I'm a professor. I could be on the committee that helps with your thesis. So there's a lot of different ways we could collaborate that is not a formal I'm supervising you. It's just an informal relationship. Very natural, happens all the time, and I'm happy to do it as well. Yeah. Okay, other questions about that? Okay, so the main point is just think of your project as a way of leveraging it. Try and think of it beyond a project itself. Can I get something beyond just a project out of this? Then it will also be a good project almost by definition if you're trying to leverage it into something else. Okay, in terms of the management of the project, I don't need anything from you other than the PDF on the final day. Okay, that's it. Okay, so you never have to talk to me about what you're doing, who you're working with, anything like that. It's completely up to you. You can self-organize. You can choose your topics. If two different people in the class do something on a project on the same subject, then there's two projects on the same subject. That's not a problem. Okay. So that said, I am here to help. It's not that I don't want to hear about your projects. I'm just saying that there's no obligation for you to tell me anything about it other than give me the report. But I do want to hear about it. So I'm here, as you know, before class, in the middle of class, at the end of class. I have office hours. I have an email account. You can ask me questions. There's a few things I won't do. So one thing is I'm not going to help you pick a topic. Okay, if you have an idea of a topic, I might help you refine it. So I might say, oh, that sounds too broad. You should narrow it. That's a very common thing that I tell students all the time. So you can run your project idea. But if you're I have no idea what to do, can you just give me a project? I can't give you a project. again, that's like 25% of your mark is just coming up with a good project. Okay, not literally, it's not like a criteria, but it's sort of, that's a lot of work that your colleagues are doing, is coming up with the projects themselves. The second thing I can't do is I can't read drafts of your projects. It's just too much work. If everyone wants a draft read, I can't get through it all. What I can do is if you give me a draft, I can look at it for 2 minutes. And if I can see something to tell you to improve in 2 minutes, I can tell you about it. But that doesn't mean that there isn't something that you should fix. It's just whatever I can see in a couple minutes by looking at it. Another thing, this is for all my courses, I usually give this advice, is sometimes a good project topic is a question. So if you phrase it as a question, then your project report is answering that question. And then it becomes a lot clearer, like, should I include this or shouldn't I include this? Well, does it help you answer the question? If it doesn't help you answer the question, you don't have to include it, okay? So it helps you like keep your focus like very narrow and you're staying on topic because everything is in service of answering the question. It doesn't have to be a single question, it might be a set of related questions. And again, you don't have to do this strictly, but it is a tip that you can consider doing that tends to help. References, any formats, and this. Okay, and the rest of the stuff I talked about last week. So if you missed that, of course the lectures are online, so you can catch up there. But this is just about the subject or the topic of the paper itself. Okay, so that's all I wanted to say. Are there questions about it? Okay, see none. All right, good. Okay, so let's jump back into the lectures then. Okay, so just as a review, last class we didn't quite make it through summarizing. Sorry, this is the wrong course. So we were going to try and summarize all the sort of primitives that you would have learned about in 6110. And we got through hashes, PRGs, extractors. We talked about encryption, but the one thing I didn't do is I didn't tell you the security definition. So what does it mean for encryption to be secure? So that's where I'm going to start. The reason I didn't do that is I wanted to first show you a MAC, because MACs are related to the security definition for encryption, okay? So we'll pick up the security definition of encryption, and then we'll just talk about 3 more things: key exchange, public key encryption, and digital signatures, and then we'll move on from there. Okay, so I'm going to start with the definition of encryption security. Yes.
Can you try this to switch colors? Maybe
Yeah,
blue on
it's-
black is very
Sure, sure.
playable.
Yellow. Yeah, that's better.
Oh, it's better, right? Okay, I won't rewrite this, but it just says security for encryption.
Okay, thank you.
And I don't know, last time was it black on the background or was it white on black?
It was blue on black as well.
It was blue on black? Okay. All right, anyways, there is a way of changing it. I'm not sure how. I think it's in dark mode because it's now night. Anyways, I'll try and figure it out for next class. I think it's probably easier to do like dark on white, but I'll keep it this way for now. Okay, first off, does anyone know, can anyone tell me what does it mean for encryption to be secure?
To have an encryption that is hard to break, so basically someone cannot easily guess what's behind what the plain text is from the ciphertext.
Okay, so a basic definition is basically I show you a ciphertext. You shouldn't be able to figure out what the plain text is. You shouldn't be able to even figure out, like, say, what a single bit of the plain text is. So that's sort of essential to the definition. But there's some extra stuff that we do in and around that definition, if anyone knows.
Security doesn't rely on the actual, like it's on the knowledge of the encryption method. So like the method has to be known by everyone, and it cannot be
Okay, yep.
cannot be based on the anonymity or whatever.
Correct. So we will assume that the adversary knows the encryption algorithm, everything about it. So it's a public algorithm. There's nothing else that's known.
I know that there was two types of encryption algorithms that were like almost impossible to decrypt. There was, one of them was the discrete log problem,
Mm-hmm.
and the other one was the factoring of a large prime number or something.
Okay, so those are two assumptions. So sometimes in security, we reduce encryption and we say breaking encryption is exactly the same as breaking this other thing. And this other thing is a well understood mathematical problem. My encryption algorithm's not really well understood, but I just proved that if you can break my encryption, you can also break this well established assumption. Okay, so two of them are discrete log and factoring composite number, a product of two primes. RSA uses the latter, things like DSA signatures use the former. So that is true. That's something we'll see. We're not quite there yet. So that assumption comes when we switch from symmetric key encryption, where the sender and receiver have the same key, to public key encryption. That's when we'll see those assumptions. Yeah. Okay, so I'm going to just define this. So the security for encryption, the way we think of it is we actually think of it as a kind of game. Okay? It's a game that's played between two people. You have an adversary that's trying to break the system, and you have another party that's just sort of, it knows the key, it knows everything about the encryption. You can think of it as kind of like the honest user, but it's also like very responsive, and it's going to let the adversary really test it. Okay, the best way to think of it is think of your computer. You just leave it open and you have your key. And of course I could sit down and try and pull your key out. But in this case, I'm not going to do that. What I'm going to do though is I can, for example, if I want to encrypt something, I'll type in the message and I'll press a button and then it's going to encrypt it with your key. I'm going to learn what that ciphertext is. Or vice versa, I could make up ciphertexts and then I could ask it to decrypt it. Okay, so imagine you kind of leave your laptop around. I don't have access to the key itself, but I have access to its encryption and decryption functions with your key. I'm allowed to use that computer as much as I want. And even then, I shouldn't be able to tell what your key is. Even if I'm allowed to ask for the encryption of any message I choose, and I'm allowed to ask for the decryption of any message I choose, I still shouldn't be able to figure out what your key is, or I shouldn't be able to decrypt a new message that I'm seeing. Okay, so that's the game that we play. The strongest version of this game, it comes in different flavors. The strongest version of the game is called, which I'll define, but then I'll show you how we can remove things from the game to make simpler definitions. It's called chosen ciphertext security. Or attack. I'll call it an attack. So security is you defend against this attack. And we call it CCA. Okay. So CCA secure is the strongest notion of security. There is a weaker notion called CPA security. And then there's an even weaker notion, which is sort of the intuition that you gave me, which just basically says you can't figure out what the key is by looking at things. And sometimes we call that OTS, one-time secure encryption. Okay, but I'll show you the most complicated one, and then we'll simplify it later. Okay, I'm going to call that thing where you leave your laptop open and anyone can ask for an encryption or decryption. I'm going to call that an oracle. Okay, so that's sort of what it's called formally. It doesn't, don't worry about the word. It sounds kind of weird, but anyways, that's what it's called. Okay, so this is what happens in the game. The adversary is allowed to send any number of messages to the oracle. The oracle knows your key, so it knows the secret key. And what it will do is it will send back an encryption of that message under that key to the adversary. I'll put MICI just for the notion of different messages, okay? And you can do this as many times as you want. Okay, then what will happen is the adversary can also, it doesn't have to be after, it can be before or during or in the middle. It can do the opposite too. So it can choose ciphertexts, and it will ask the oracle to decrypt them, and the oracle will decrypt them using your key. Sorry, this should be CI.
This is assuming there's only one key?
Yep, assuming there's one key, sure. Yeah, so the goal is to, well, you see what the goal is yet. I haven't said what the goal of the game is yet, okay? But this is just something you're allowed to do.
This is symmetric?
And this is symmetric key. But CCA actually, it doesn't, it's the same definition for public key. Okay, just let me get to the end of the game and then I'll answer that question. Yeah. Okay, so this is the actual game part. So this is kind of like a preamble. It's stuff you can do at the start of the game. Then the game itself, to test whether you can break the encryption or not, is what the adversary is allowed to do is choose any two messages. I'll call them M1 and M2. Okay? What the oracle will do is it will flip a coin and choose, I'll call it M star. So M star will either be M1 or M star will be M2. So it will flip a coin. It will either take M1 or M2. It will send you back an encryption of that message that it chose. So I'll call it C star. So it's an encryption under the secret key of either M1 or M2 based on a random coin flip. The adversary doesn't know which of the two. Okay? Then what the adversary is allowed to do is they can actually do this again. So now that they've seen this challenge ciphertext, they're allowed to, again, ask for any encryption or any decryption that they want. And then they have to guess whether the oracle sent them M1 or M2. Okay? Let's say they can break encryption. Let's say they can recover the key. Do they know whether the oracle chose M1 or M2? If they can break the key, they know, right? They can just decrypt C star under the key and they can figure it out. Okay? Let's say that they can't break the key, but in fact, they can't even figure out what was encrypted, but they can find some little tiny piece of information. Like, I can figure out the first bit of the message. I can look at the ciphertext. I don't know what was encrypted, but I can at least figure out if the first bit was a 0 or 1. Okay? I can win this game. All I do is I send one message that starts with 0. I send another message that starts with 1. And then when I get it back, I decrypt that one bit of information that I know. And then now I know whether it's M1 or M2. Okay? So what this game is meant to capture is like every possible way that you could break encryption. You can turn into a strategy to win this game. And if you win this game, we say the encryption is insecure. Okay? So if you can even decrypt a single bit, it's considered insecure. Okay? So the definition of security for encryption is that no adversary can ever win this game. And what does it mean to win? They can guess. They'll be right. I mean, you just guess M1, M2. You have a 50-50 shot of being right. Okay? So to win the game, what you have to do is you have to demonstrate that you can beat it 50% plus some amount. Could be 1%, 60% of the time. Doesn't matter. Some non-negligible amount above 51 or 50%. Then we say that this encryption is insecure. Okay. Now, normally people, they don't literally play this game. They don't sit with AES and get it to like do this stuff and do it. They work out a theory of how to break it, and then they prove mathematically that in theory it's going to create a strategy that lets you win this game more than 50% of the time. So most of the breaks happen sort of with pen and paper. It's not like a literal game. It's like a sort of conceptual game to help you think about what the security of it looks like. Okay. So let me just finish off the game. So again, we get another stage where we can do this again. But we add one restriction. Otherwise, the game would be trivial to break. So the restriction we add is if you ask for the decryption of messages here, you cannot ask for C star. Okay, so you got this C star, this challenge message. You're not allowed to ask for the decryption of C star. Otherwise, that would trivially break it. Okay, so here, this can be any ciphertext except C star. Okay, and critically here, you might say, well, what about M1? Can I ask for M1 and M2, the ones that I used in the challenge? Can I use it? And you are allowed to do that, though. Okay, so here you can use M1 and M2 if you want to. Okay, and the security is basically it's CCA. Let me put it the opposite way. So I'm going to break CCA security if I can win with greater than 1/2 plus, we say epsilon, and epsilon just means a negligible amount. I won't get into the definition of it. You'll probably learn it in 6.110 anyways. Just means like a really small amount, okay? It's because sometimes you might get lucky and you might win a few more times. But eventually over time, if you run this experiment along enough and you don't actually have the ability to break it, the probability, your win success will converge to 50-50, a half, because you're just blindly guessing. Okay, now let's think about a few things that, a few kinds of encryption at a high level that aren't going to pass this test. Okay, so last class I talked about there's modes of operation, right? And I talked about something called ECB mode. And in ECB mode, if you put the same plain text in, you get the same ciphertext out. Okay, so every time I encrypt the message that's all zeros, I always get the same ciphertext. And every time I encrypt the message that's all ones, I always get the same ciphertext. Okay, if that's the case, if that's true about encryption, can I beat this game? The answer is yes, it's pretty easy. What I'll do is I'll ask for an encryption of all zeros. I'll write down what the ciphertext is. I'll ask for an encryption of all ones. I'll write down what the ciphertext is. Then I'll go to the challenge stage and I'll say, okay, my challenge ciphertexts are all zeros and all ones, and I'm going to get back a ciphertext that's one of the two. Okay, so I immediately know which one it is. I can win that game 100% of the time. Okay, so a few things. So, yeah.
The M1, it's M1 or M2 that you're sending on the stream, right?
So I'm sending both.
You're
Sorry.
sending concatenated together?
Yeah. Well, yeah. I mean, it has to parse them out because it's going to choose between them.
Oh.
Yeah. But yeah. So I'm sending both M1 and M2. Yeah. Okay. So a necessary condition for CCA security is randomized encryption. So if my encryption isn't randomized, if it always gives me the same ciphertext, I'm never going to meet this definition of CCA secure. Okay. Now there are weaker definitions of security. So if I'm going to use a different color here, but if I were to drop these two parts, then CCA would turn into what we call CPA security. And so that's a weaker notion of security. It stands for chosen plain text attack as opposed to chosen ciphertext. So here I'm choosing plain text. I'm allowed to ask for their encryptions. I'm also allowed to choose ciphertext and ask for their decryptions. A weaker version, I'm just allowed to ask for plain text, not ciphertext. So there are some encryptions that are CPA secure, but they're not CCA secure. For this course, I don't care. Like, we're never going to need something that's only CPA secure. Okay, everything that we're going to see in this course needs to be CCA secure. Okay, so this is just for your interest. And then there's even weaker ones that aren't even CPA secure. I will show you one example of that because it's an attack. So there was a flaw in a protocol that we'll talk about hopefully today called TLS. And because of that flaw, they thought it was CCA secure, but it turned out to not be CCA secure, and that let people break the encryption. So I'll show you something that went wrong. But anyways, okay. There's a second component to it. Which is, last class we talked about encryption and we talked about MACs. MACs are, if I send you a message with a MAC, then you can tell if someone modified it in the middle, okay? It turns out that if you want CCA secure encryption, you have to have a MAC as well, okay? If you don't MAC it, you're never going to get CCA security, okay? So you need to have authenticated encryption is what we call it. It can be with a MAC itself. So a lot of protocols are going to encrypt in MAC or MAC and encrypt. The order matters a little bit. And then some modes of operations sort of have a MAC that's kind of built into them. So the example I gave is there's something called GCM, which is what we'll see later. And this is just, it has a MAC built in, basically. Okay, why do I care between the two? If I MAC it and then encrypt it, I have to go across the data twice. I have to go through once to MAC it, and then I have to go through it a second time to encrypt it. If I use one of these mode of operations, the main thing it does is it lets me just do one pass. So I go through, I encrypt it and MAC it sort of simultaneously, and then I can just pass through the data once. So it works better in like a streaming case where data is being streamed to you. So that's the difference in terms of security is the same. Both of them are CCA secure, but this one is just a little bit better in terms of performance. Okay, let me give you a simple argument for why this is the case. Why does it need to be authenticated? So back to the game. Imagine I have ciphertexts and they consist of two kind of components, two blocks, if you will. So blocks of 256 bits. Okay, actually, I'll put it as messages instead. So I have M0 and M1, and they're both 2 blocks long. Okay, in M0, what I'm going to do is I'm going to put it, just going to fill the first block with zeros, and then I don't know, I'll put some other garbage here, doesn't matter. Second one, I'm going to put a bunch of ones here, and then I'm going to put a bunch of garbage here. Okay, I'm going to send these to the Oracle. M1. The Oracle is going to pick one at random. I don't know which one it's going to pick, and it's going to send me an encryption of it, C star. Okay. Now I'm allowed to ask it to decrypt any ciphertext I want, except for C star. I can't just ask for it to decrypt C star. So what I'm going to do is I'm going to look at C star, and I'm going to notice that, you know, encryption preserves length. So whatever the message was, it's going to be like 2 blocks as well. And what I'm going to do is I'm going to go in here and just like flip a bit. Okay, so I'm going to call this C star prime. Is C star prime the same ciphertext as C star? It's not, because I flipped a bit, so it's technically a different ciphertext. So I'm allowed to ask for the decryption of that. Okay, so what I'll do is I'll send that ciphertext here. Okay, then it's going to send me a decryption. And here's what I'm going to see. I'm either going to see the first block will be all zeros, and then there's going to be some other block that's different than this one because I flipped the bit here. Okay, I flipped the bit here, it kind of ruined this block, so this block is going to be different. Okay, but the first block, because I didn't flip it until the second block, the first block will be preserved. Okay, so I'll see that it was all zeros, or I'll see the first block was all ones, and then I'll see some garbage in the second block after I flipped it. Okay, based on this, do I know whether C star was M0 or M1. I do because I can see the first thing. Okay. How do we prevent that? I want to be secure against this. I don't want this to happen. The idea is that what I'll do is I'll throw a MAC in as well. Okay. So when I have a MAC, what happens is when I go to this ciphertext and flip this bit, the MAC is no longer going to match. Okay. So what will happen is the oracle, instead of sending this back, it's going to send back. Okay. So this, I'll put this without a MAC. If I do this with a MAC, then the oracle is going to send back error. Okay, you sent me this ciphertext. This is not a valid ciphertext. It doesn't have a valid MAC anymore. So if you change even a single bit of a message, it ruins the MAC on it. All right, and so this isn't going to verify anymore. So I can't win this game anymore because every time I try to modify the ciphertext it gave me, I'm just going to get error, 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 error. And it's really, really hard. We said the definition of a MAC is I can't even come up with a message that matches this MAC, essentially. Okay, so anyways, this is why we need both of these two properties. This is maybe a little more detailed than you needed today, but when you take 6110, you'll hopefully see these games and like kind of understand those security definitions better. Okay, any questions about the game or the definition of security? Yeah.
First of all, why do we flip the page, and what is the point of using the MAC here?
Okay, so we flip the bit because we're not allowed to ask for the decryption of C star. But what I'm trying to do is I'm trying to get a ciphertext that's so close to C star that I'll still be able to recognize it. So I don't necessarily have to flip a bit, but this is a sufficient thing. So it's a minimal change I can make, so it's technically not C star anymore, and I can flip it.
But the
Yeah.
thing is, you have put here the input as a garbage.
Yeah.
Then again, you are flipping it.
Yeah. So I just sort of did this off the top of my head. Let me do this slightly different. It ends up being the same thing. Let's say that I actually start with all zeros. So I have 2 blocks of all zeros, and I have 2 blocks of all ones, right? So what will happen is because I flip in the second block is going to turn into whatever it does, but the first block is going to be okay, yeah? So I'll still be able to recognize which of the 2 it is, yeah? So this is true of most encryption schemes because when you encrypt more than one block, they kind of chain it together. So they take the first block and they encrypt it, then they kind of feed that into the next one, and then it works kind of sequentially. So you'll see this in 6110 if you look at modes of operation. But anyways, for now, you just need to know that if the encryption scheme imposes a MAC or authentication, then this game, you can't win it anymore, which is what you want. You want a game that you can't win because that means it's secure. Okay, there was another question? Yeah.
Why does it break the game if we ask for C star, but it doesn't break the game if we ask for M1 or M2?
Okay, so C star, the challenge is about recovering a message from a ciphertext. That's the nature of the challenge itself, right? And so that's why we can't ask for C star. But the nature of the challenge isn't about predicting what ciphertext would come if I ask for messages themselves. So that's why I'm allowed to do one but not the other.
But if we ask for M1 and then we find C star, we are able to tell whether the message we got was M1 or M2.
Okay, so this is the point here of, I didn't explain what randomized encryption means, but that's true if the same message under the same key always gives you the same ciphertext, yeah? So what I'm saying is if you want CCA secure, you have to have an extra property where if I encrypt the same message 10 times, I get 10 different ciphertexts, yeah? Okay, so that question is exactly why we need this property called randomized encryption, yeah, which is if I encrypt the same message 10 times, I get 10 different ciphertexts, okay? And I can't even relate them to each other. Okay, any other questions about the game? Okay. Okay, so let's move on to 3 other primitives. So we're going to move into this sort of public key space. And let me do key exchange last. Since I usually do it in the other order because I'm showing you how they work on the inside. So I'm going to start with public key encryption. Okay, so public key encryption is a function. It takes 2 parameters, generally maybe 3. So the parameter would be the message that you want to encrypt, the key that you're encrypting it under. I'm going to call this a public key. I'll talk about what that means in a second. Public keys have a certain length. I'll just denote it as L. Messages for public key encryption actually are generally limited. Okay, so they can't be arbitrarily big. So they'll have some size. Usually the size is the same as the key. I'm not sure how to denote it. I'll just denote it as M. Technically, it's not like a length based on bit string. It's based on the underlying mathematics. So it's taken mod P, where P is a prime number, mod N. But anyways, it doesn't matter. The point for you to understand is that the messages are limited in size. Okay, is that going to be a problem? Let's say I want to encrypt with a public key encryption the contents of my hard drive and send it to you. It is going to be a problem. Okay. What I'm going to do instead, I'm never going to do that. What I'm going to do instead is I'm going to pick a symmetric key. I'm going to encrypt the symmetric key with the public key. The symmetric key will fit in this message, and then I'm going to encrypt my hard drive with the symmetric key. So I'll give you both. You'll decrypt the one to get the key for the other. Okay, you're going to see an example of that when we talk about HTTPS. What is which? Just the length of the message. Sorry, this M here? Yeah, I meant just the length of the message. I can call it whatever variable you want. Let's call it K. I'm just trying to denote that it's not infinite. So before, when we looked at symmetric key, we said it can be any length.
Okay.
Yeah, so for public key, it is limited in length. Yeah.
Is there a reason why we cannot do chunks also with this one?
You can. So you can, whatever you do with your block cipher, if you want to chunk it and chain it, you could, in theory, do it with public key encryption. So there isn't a reason why you can't do it. The reason people don't do it is for performance. So this is 1,000 times more expensive than a symmetric key encryption. Yeah. So it's still very fast. Your computer can do it pretty fast. But if it has to do a whole bunch, then you're going to start feeling it. And so that's why. Yeah. Okay. And then you may or may not have randomness. So we actually had just talked about how we would want randomized encryption if we want CCA security. So you could have a random factor as well. The output will be a ciphertext. The ciphertext size call that R. Because of the randomness, it's actually going to be K plus R. So however big your message is, you're going to have a ciphertext that big, and then you're also going to have a bunch of bits to correspond to the size of the randomness itself. This is a small point. Don't really worry about it. The ciphertexts aren't infinite. They're the same size as the message, but if it's randomized.
Infinite?
Pardon?
Infinite, you said?
So it's not infinite. It's not infinite. Yeah, that was the point. Yeah.
Randomness is the salting.
Yeah, so you can think of it as salting. Salting is, so sometimes we have different words that we use for randomness. So you'll see a word like salt. You'll see a word like knots. You'll see a word just like randomness. The thing you have to think about is it going to be a secret or not? So generally when we salt things, the definition of salt is it's not secret. So we salt it and then we actually store the salt value beside the thing that we just salted. Yeah. So it's sort of like a salt, but in this case, I'm not going to send the randomness as well. I'm just going to send the encryption across the wire, and I'm not going to send the randomness as well. If it was a salt, then I would think I'm sending the salt along with it. Yeah. Okay. All right. Then we're going to have a decryption algorithm.
According to the function, the randomness is inside the function, right?
Yeah. So it's something that the person who's doing the encryption chooses. So I'm going to encrypt a message. I'm just going to choose some randomness or have my computer choose it. And the main property the randomness gives you is just that if I encrypt that same message 100 times, every time I'll get a different ciphertext because I'll change the randomness myself when I encrypt it. Yeah. Functions themselves, we don't generally in cryptography think of functions as being random. So a function is written down and it always works the exact same way. So if we want random behavior, we have to supply it as an input to the function. We can't rely on the function itself to do it. Okay. All right. There's going to be the opposite, so I'm going to be able to get this out, the message back out. So to decrypt it, I just need C, and I need what's called the secret key. If there's randomness used, I don't need it at decryption time. Okay, it will cancel out somehow, and it will disappear. I just need the secret key itself. Okay, now what's a public key and what's a secret key? So this first off should look just the same as symmetric key encryption. We didn't necessarily denote randomness, but there is randomness. We call it an initialization vector or an IV. The only other difference is just that these keys are different. Okay, so we call this asymmetric encryption because the key that you use to encrypt is different than the key that you use to decrypt. And if you know the key that you use to encrypt, you can't find the key to decrypt. Okay, so you can start with a secret key and turn it into a public key, but you can't start with a public key and turn it into a secret key. Okay. Why can't you do that? Because there's some hard math problem like the discrete log problem or factorization that stops you from doing that. Okay. What's really great about this is I can put my public key on my website or wherever and just say, this is my public key. You have a message for me, use it, encrypt it. I have the corresponding secret key. It's on my computer. I never share it. It's like locked up by Apple and there's like secure enclave. And when I get one of those ciphertexts, I put my fingerprint on my computer, it goes and fetches the key and it decrypts it.
SSH works like this too, right?
Sort of. So SSH is going to be something that we'll see HTTPS and SSH is almost the same. It's going to, this is going to be a piece. It's going to be one piece of the whole protocol.
So this could be RSA.
Correct. Yeah. So this is RSA. Yeah. So RSA we generally don't define with randomness, but when we use it in practice, we do put the randomness there. We call it padding, and there's a certain standard that tells you how to pad RSA to get that randomness there. Otherwise, it won't be CCA secure. Yeah. So if you know RSA encryption, this is RSA encryption. If you know LGML encryption, this also matches LGML encryption. Those are the two probably most standard ones. Okay.
So it's factorizing.
So RSA is based on factorizing, and LGML is based on discrete logarithms. Yeah, yeah. So I won't talk about what those are in this course. I don't think. Maybe we'll need them at some point. But
we took them already.
yes, yeah, exactly, yeah. Okay, we're missing one algorithm, which is just how you do this step. So we call it key gen usually, and so the first thing I'll do is I'll compute my public key from my secret key. So I'll choose a secret key at random. I'll have my computer choose it completely at random using one of those random protocols that we talked about last class. So this will be random. Yep, yep. Yeah, so you can use SSL, OpenSSL to keygen or whatever, yeah. And it will pick one at random and it will give me the public, it will tell me both of them because I'm going to need the secret key when I decrypt. But then I'll take the public key, I'll tell everyone what my public key is. Now you can all send me messages, only I can decrypt them, okay? And we don't have to have the same key anymore, okay? So there was an earlier question, I think last class, of like, how do you find someone else's key, right? So this kind of solves the problem. I have a public key, I tell everyone about my public key. Now they know my public key, so they can encrypt messages for me. And we still have that question of how do you learn my public key? That's a critical question that we'll deal with, okay? But now that you have my public key, you can send me a key. And normally what you would do is you would just pick a symmetric key and send it to me using my public key. And then now we both know a symmetric key. You know it because you chose it. I know it because you sent it to me through public key encryption. And now we can do encryption a lot faster. So instead of chaining together or blocking together public key encryptions, what we do is we switch over to symmetric key encryption because it's much faster. Okay, we'll see those details later. Okay, any questions about public key encryption? Okay, and again, the security of it is the same. So you can go back to that CCA game. So it's the same definition of security. Okay, we have signatures. So signatures are kind of like they're public key MACs, basically. They do the exact same thing as a MAC. They're just a public key type of thing. So I have the exact same algorithm. I generate a secret key, I pick a secret key at random. And I generate a public key from it. You can literally use the same secret key and public key as you use for encryption if the underlying algorithm is the same. So RSA is the name of an encryption algorithm. An RSA key works. There's also a signature algorithm called RSA. The keys are exactly the same. Generally, it's not advised. It's better to pick one key for encryption and a different key for signatures. There's some reasons why I won't get into, but technically you could. Similarly, if you're using AlgoML here, and your signature algorithm is Schnorr or DSA or ECDSA, then you could literally use the same public and secret key. Not advisable, but you could do it. Okay, so with signatures, we have an algorithm. It's called sign. It's going to take a message, and it might take randomness as well. And this time it's sort of the opposite, where this is going to be the operation that's locked, that only I can do. So it's going to rely on my secret key. So I'm the only person that can sign a message. It's going to output a signature. Normally we switch to Greek letters, so I'll call it sigma. And all the other things are the same in terms of the input and output sizes, with one exception, which is the message. It does sometimes make sense to sign big messages. So public key encryption we really use to just send around symmetric keys, which are short. But sometimes when I want to sign something, I want to sign a document, I want to sign a movie, I want to sign a piece of software, right? You've heard of code signing. So if I send a software update to you, I put a signature as a developer, or Microsoft or whoever's giving it to you, they put a signature across that entire file. And that file could be big. It could be gigabytes. Okay? So what I need is the message to be as big as I want. But the problem I have is the signature algorithm expects a message that's inside the math that it's using. Okay? It doesn't support arbitrarily big messages. Okay? So can I have both? Can I live in both worlds where I can have a signature scheme that wants a small message, but I can sign messages as big as I want? So there's one stupid trick, right, that fixes this, and that is I first hash the message. Okay, so I take the message, I hash it. Now it's a short fingerprint. It's short enough that it fits inside the math of the digital signature. Then I can sign the hash of the message instead. Okay? Now, is this secure? Is it as good to sign a hash of a message as signing a message itself? Well, remember, one of the properties of a hash function is called collision resistance. You cannot find two messages that hash to the same thing. So if I have some software that I signed, you want to create your malware version of the same software, and if you can make it hash to the same value as mine, then the signature on the real software, you can lift it off and put it on the fake software. But the properties of hash functions say you're never going to be able to do that. You're never going to find that second piece of software that produces the same hash, even if you spend the lifetime of the universe using all the supercomputers in the world trying to find it. Okay, so that's why it's a secure paradigm. So it relies on collision resistance, strong collision resistance of the hash.
So if the message is too big to sign it, we do the trick
We just hash it and then sign it, right?
Yeah, actually, so what we do is we just hash it anyways. We don't even worry. Like even if we could sign it directly, because then the recipient has to decide. They have to know whether it's big or small. Yeah. So it's not a security thing. It's just it's easier on the recipient side if everything is done the same way. Let's put it that way. Yeah. So you don't have to worry about two modes of it. Yeah.
So they always hash.
Yeah. So they'll always hash it. Yeah. Sometimes when you look inside the signature algorithm, the hash is actually part of the signature. Like it's something you're doing anyways inside of it. So signatures like DSA, Algamel, Schnorr, you're doing the hash anyways, and you just sort of shovel the message in with the hash. Things like RSA, it's more of an explicit, I'm hashing it first, and then I'm RSA encrypt signing it. But, yeah. Okay, then a signature, we're going to have a verify function. So I want to check whether a signature is correct or not. What I need is I need a copy of the message. I need a copy of the public key of the person who supposedly signed it, and that's all I need. If there's any randomness, I don't need a copy of it. And then it's just going to output true or false. So yes, this message, I need the signature itself, obviously. Okay, so the algorithm will just say, yeah, this signature is a signature on this message using this public key. Okay, and it's very robust. If I change a single bit of the message, the signature gets completely ruined. Okay, if I change a single bit of the public key, or I have a different key or anything like that, if anything isn't bit for bit an exact replica, then it's not going to verify. So it's only going to verify if it's exactly correct.
Sir, what is this?
True, false. This part, yeah. Or sometimes we say accept, reject, same idea. Okay, then the security definition is, it's defined almost like the CCA game. I'm not going to write out the full game. I'll just say it's kind of like the CCA game. Basically, you have an adversary, you have an oracle. The adversaries can ask for the signature of any message. Okay, so they can pick any message they want. They can get a signature on it. And then the challenge for them, it's not like an either or thing, but they basically have to produce a message and a valid signature and have this verify. Okay, so you can play with it. Like say you leave your laptop open, I can sit down at your laptop. Pardon?
They choose the message?
Yeah, so the adversary can choose any message they want.
Selective forgery.
Yeah, so there are differences between selective and universal forgeries. And that's sort of akin to the difference between the CPA game and the CCA kind of game. Yeah. So for the purposes of the protocols that we will look at, we'll always assume the strongest security from it. We won't differentiate between the two. Yeah. So it's so it's secure against any kind of forgery.
Forgery also, right?
Sorry?
There's another one, extension forgery.
There's existential, selective, universal, I think. Yeah. Okay, anyways, we'll assume the strongest version of security. Okay, the last thing I want to talk about is key exchange. Unless if there's other questions about signatures. Okay. Okay, so key exchange is a sort of alternative to the protocol where basically you have two people like Alice and Bob, and they basically want to decide on a key, and there's an adversary in the middle. So there's an adversary here. I'll draw devil horns for adversary, and they can intercept every information that goes by. A and B will exchange information. For this to work in its strongest form, both of them will have public keys, and they'll both know each other's public keys. Okay? So they're just going to send some information back and forth. They're going to sign it. The other party is going to make sure that the things are signed.
Same as Diffie-Hellman, right?
So Diffie-Hellman is this protocol, an example. Yeah. So it's Diffie-Hellman with the signature based on it. Yeah. And then at the end of the day, they both will have a key that they can agree on. So they'll have a copy of the key. Bob will have a copy of the key. The keys will be the same, so it's a symmetric key. Okay. And then they can turn around and they can start doing other things. Okay. How does this work inside? It's sort of simple and sort of complicated. So Diffie-Hellman, it's pretty easy. You can write it out. It's just like 3 numbers. But the reason why those 3 numbers give you these properties is harder to understand. It's based on the discrete logarithm problem that a few students have mentioned. So you'll see it in 6110. We're not going to worry too much about it, like how it works internally. Just know that, yeah, 2 parties with public keys, they send some messages back and forth. Even though someone's listening to everything that's said, they can both derive the same key, and the adversary in the middle has no idea what the key is.
But the key is asymmetric, right?
So the key is just, think of it as a random string. Yeah? So
The public key,
you could turn around and use it for that, yeah.
but the public key is something that everybody could know, right?
Everyone knows the public key for all the parties, including the adversary.
Certificate, right?
So that's another thing that's sort of related but sort of different, yeah. Something that we will talk about in a sec. Okay, this protocol, so Diffie-Hellman, was invented in 1976, 77, before even RSA. It's like the original crypto protocol, and people thought this was an impossible problem. So they thought, it's impossible. You can't have 2 people talk and somehow come up with a secret and have someone in the middle who literally can read every single thing, and yet somehow they can both know something and the person in the middle doesn't know it, right? That sounds like fundamentally impossible, okay? And so it was a huge breakthrough when someone solved this problem. And the intuition is sort of you kind of hide values in a hard math problem. So you take some secrets, you put them in a hard math problem, you kind of send it, the other party does the same thing, and then you're able to combine what you know and what the party gave you in order to derive the same value on both sides. Yeah, and so then it works, and it's kind of magic, but anyways. Okay, so this we may at some point look at Diffie-Hellman, because sometimes when we look at authentication protocols, they go into the details of how this works. For now, for today, I'm just going to leave it at this, and then later, if and when we need that, then I'll show you what that protocol looks like. But for now, we'll just sort of believe that it's the case.
3 paths, right?
Yeah.
Yeah, so there's different variants of it, yeah.
And it's similar also to Algamel, right?
So Algamel is an encryption that's based on this. So it's sort of like you just kind of toss a message in.
Who invented Algamel is the student of one of these 2 scientists who did Diffie-Hellman.
That's possible, so I'm not
Yeah,
sure, but
before.
yeah, okay, yeah. So probably the Hellman didn't really get involved in crypto after this protocol, but with Diffie was around for a while, and yeah, Algamel might have been a student. Okay, questions about any of this, because we're now done our 6110 review. So now's your chance to ask any crypto questions.
So this course is going to incorporate like all those things that you mentioned? Follow up on that?
Yeah, exactly. So the very first protocol we're going to look at is HTTPS. It literally uses every single thing that we just talked about. Okay, so we're going to combine all of them and make a protocol out of it. So that's actually why I wanted to go through them one by one and make sure we're solid about each of them. So there was a question too before the class of is this going to be on an exam? So I'm not here to test you on 6110, but because something like HTTPS uses all of it, right, then you need to know this stuff in order to answer questions about 6110, or sorry, to answer questions about the protocols that we'll look at. So you'll be tested indirectly on it, but not directly. Okay, any other things, questions? No? Okay, yeah. Yeah.
Did you decide a date for the midterm yet?
Yes, I did. I decided to do it. Some people wanted it late because of travel, and so I decided to put it on not the week. So there's reading week, then there's a Tuesday that's right after reading week, but it will be the following Tuesday. Yeah. So I forget what date that is, but yeah. And then I won't test you on everything up to then. I'll probably just test you on from the midterm before. So like whatever we learn in the week between reading week and the exam won't be on the exam itself. Yeah. I'll update Moodle and I'll put those dates on. Maybe I'll do it during the break because that's where I was going now. If there's no other questions, let's take 10 minutes and then we'll come back.
About the exam format, like
For the format, so it could be short answer, it could be multiple choice.
one of them or together?
Sorry?
The two of them?
The two exams or the two kinds of questions?
The two types.
Yeah, there could be both types on an exam. Yeah. So I haven't decided. Like I say, I've never taught this course before. This course is more about like protocols and crypto. So normally I like multiple choice, but I'm not sure I can always condense a question into a multiple choice for this kind of thing. So there will be some multiple choice for sure that are more conceptual, like making sure you understand the concepts. And then being able to follow a protocol might require you to write some stuff out. So definitely the final will be a mix of the two. And the midterm, I might just, if I can get away with just a pure multiple choice, I'll do it. But I'm not sure. I don't know whether I can or not. I have to write the exam, yeah. Okay. Other questions? Okay. So come back in around 10 after 7. Okay, so now we're going to switch gears a bit. What I'd like to show you is a protocol for forming what you can think of as a secure tunnel. But we're going to take a little detour before we go back into the crypto. But I'll just sketch out what we're doing first. The protocol we're going to look at is called HTTPS. And this is a protocol I also spend a lot of time on in another course I teach, which is called INSE 6150. Some of you may have taken it. In that course, I focus on kind of an issue called PKI. I'll mention it here, so we'll talk a little bit about it. What I don't do in that course is go through the crypto itself. And so here I'm going to focus more on the protocol and not talk a lot about the PKI. Okay, so if you want a complete picture of the protocol, you could look at both of these things, but obviously it's not required for this course to understand what's being taught in a different course.
150 also mainly focuses on HTTPS?
No, it doesn't mainly focus. It's just one example, but there's 3 lectures out of 12 on it.
But as you said, it's far away from crypto.
Yeah, so it focuses on a different issue, which I will identify here. I'm not going to spend as much time on it here as well. Yeah. Okay. So actually, I can show it to you in 1 second, more or less what the picture is. Okay, so here's the idea. You have Alice. You have some web server. Say it's concordia.ca. And what you want to do basically is you just want to send messages back and forth between Concordia. But what you want is you want a sort of secure tunnel so that if there's an adversary that's on the wire somehow, so there's an adversary here, then they don't know what you're talking about. Okay, so if you're sending passwords, you're sending credit card numbers, you're sending files, and you don't want the adversary putting malware in the files.
Like a man in the middle.
Yeah, exactly. Yeah.
There's something called SSL strip.
Yep.
That can actually like, you know what that is.
Yeah, yeah. So SSL strip is something that we actually talk about in 6150. We won't talk about here, but yeah. I'll post some YouTube lectures on the Moodle if you're interested in these lectures. But anyways, it goes through those details. Okay, so we have an adversary. The adversary is in the middle. Despite the fact that they're in the middle, we should still have secure communication between the two. Okay, sound good? All right. Now this is premised on Alice knowing Concordia's public key. Okay, so Alice needs Concordia's public key, then this will work. If she doesn't know Concordia's public key, it's not going to work. Okay, how does Alice learn Concordia's public key? That is PKI. So PKI is the question of how do you figure out whose public keys belongs to who? Okay, we don't live in a world where we have a telephone book for public keys where you can look someone's name up and get their public key. We need some other way of assigning these keys and discovering them. And so we call that public key infrastructure, or PKI, and it's all about how you swap them. And it turns out that there's a lot of problems with the PKI that HTTPS uses. And if you want to attack the protocol, the best way to attack it is probably not to try and break the crypto. It's probably to try and just get your key, get the adversary, or sorry, get Alice thinking about your key instead of Concordia's key. And then they'll make a secure connection to you instead of the adversary. Okay, so we'll talk about, I'll give you a lightweight treatment of these issues, but I'm not going to go into a lot of detail here, but I do a lot of detail in the other course, 6150. Okay, questions about this basic setup?
So our secure tunnel is the HTTPS, right?
Yeah, okay, yeah, so HTTPS, I didn't really define it. So HTTPS means HTTP secure. HTTP is the protocol you use just for fetching websites. So you've seen it, you've typed it in maybe before, HTTP:// whatever. So it's just the protocol that websites go back and forth over. How it makes the tunnel is it uses encryption. So you're basically running HTTP back and forth, but you're running it underneath an encryption algorithm or a protocol. And that protocol is called, it was called SSL and now it's called TLS. Okay, so, and in this class, what we're actually going to talk about, if you want to get technical about it, is we're talking about SSL TLS. So we're talking about the crypto part of it. And then you can use this crypto to secure HTTP, then you end up with HTTPS. Okay, you can use it to secure other things as well. So TLS SSL is used for other things other than HTTP. But anyways, we'll consider it. It's easiest to think about HTTP because it's something we're all familiar with. Okay, all right. So what I want to do is I want to take a small detour, maybe a slightly longer detour, but it's something I think that's important to understand in this class. And that is, in this setup, we assume that there's an adversary in the middle. Okay, so there's an adversary. The adversary can read and write any data that's flowing back and forth. This is a networking course, so let's assume that this is a user accessing a website. How reasonable is that assumption? How easy is it for an adversary to get in the middle of some communication? If it turns out it's really hard, like I have to spend $1 million and have a supercomputer to do it, then maybe I don't need this tunnel. Right? I'll just rely on the fact that people aren't walking around with millions of dollars in supercomputers. Okay? Conversely, if it's very easy to get in the middle, then this protocol is now really, really important. Okay? So I want to motivate the idea that it's on the easier side as opposed to the harder side to get in the middle of communication between. Okay? So the first question I have is, how do I get in the middle? So we talk about a man in the middle attack. It doesn't have to be a man, obviously, but that's the attack, that the name that most people use. Let me switch back to white. Okay, and so my question is how to get in the middle. There's a bunch of different ways. I just want to show you one. If you see one and understand one, then you can kind of understand how it might work in other parts of the protocol itself. Okay, so let's think first about sort of how, like what's sort of happening when I want to go to concordia.ca. Okay, so this is Alice. This is the web server. Alice types into her browser www.concordia.ca, presses the button, enter button. Okay, what happens? What's the first thing that happens?
DNS.
Okay, so the first thing is Alice wants to send a request packet. Even before that, I guess if it's going to set up a secure tunnel, it's just going to say, hi, I want to talk TLS. But it has to get that packet to Concordia somehow. If you drop a packet on the internet that's just labeled send it to concordia.ca, the routers, they don't know what to do with that. Okay? What they want instead is something called an IP address. An IP address is like a telephone number for addresses. And so what I need to do is I need to convert that domain name. So this is called the domain. Into an IP address. And I somewhere wrote down Concordia's actual IP address, so I might as well make it correct. So as of yesterday anyways, it was 132.205.244.185. By the way, what if you just type that in a web browser and press enter? It will take you to the website. Okay, so this IP address is indistinguishable from the domain name. The domain name is just human friendly. You can remember it. I'm not going to remember this number.
Yeah, you wouldn't write the IP address.
Yeah, so I won't. Yeah, so I'm not going to write it. So instead, I'm going to rely on someone to convert between the two. Okay, so that who converts? So it's a service called DNS, domain name service. So domain name service, DNS. At some point, we might take a deep dive into how DNS works. It's important network protocol. For now, we're just going to sort of treat it like a black box. So it's a server. It's given to you by your ISP generally. So if you're, say, Alice is on Videotron, then Videotron will say, here's a DNS for you. You don't have to use it. You can use any DNS you want. You can use Google's, for example, at 8.8.8.8. But anyways, and then you're going to ask it, and you'll say, give me the IP for Concordia. And then it will send back the actual IP address. Okay. Now you have the IP address. You can put a packet, and you can put the IP address on the outside of the packet, and the internet will figure out somehow how to route it. Okay. It's sort of it's based on a hierarchy. So it will look at the address and it will look at the most significant bit parts, and it will say, okay, all the packets that start with 132 go this way, and all the packets that start with another number go a different way, right? And then once you're in the people that control 132, then you'll keep parsing down, and then eventually you'll end up where you need to end up. Okay, we are going to sweat those details slightly in a second, but for now I'll just leave it at that. Okay, so this is now routable. Okay, who's on the middle between Alice and Concordia besides DNS? So now I've got the IP address, so I'm happy. Okay. All right, so we have routers. Give me an example of a router, or what does that look like?
Yes, the router and the website's router.
Okay. All right, so the website's going to have its own network, and there's going to be a bunch of routers. And Alice will have some stuff as well. So let's start on the Alice side. What could that look like?
Wi-Fi.
Okay, so let's say it's a Wi-Fi kind of scenario. So the first thing that I might hit is the Wi-Fi router. Okay, so Alice will send it it will hit a Wi-Fi router. I'll just keep drawing these things. Okay, so that could be Concordia's Wi-Fi. It could be maybe she's at home. It's her Videotron Wi-Fi. Okay. Can you have more than one Wi-Fi router in a network?
Yes.
You can. Even at home, you might have like repeaters or that type of stuff. Okay. So what order does your packets go through all your Wi-Fi routers?
Closest one.
Closest.
Okay, so it will find the closest one in proximity. That's what your computer will prefer. Okay, so it's going to connect to the first one, and then it's going to connect to the closest one. Then the closest one is going to find the one maybe that's next close. It depends on how it's set up, but eventually it's going to find the one that's next to your internet wire. Okay, so you'll have like the wire that comes into your house, say or your apartment or condo or whatever. It's given to you by Videotron or Rogers or Bell or whoever your ISP is. Okay, and there's a device called a modem. And the modem basically is the interface between their cable and your network. And then you will either have a combination router, so they'll give you something that's a Wi-Fi router and a modem all in one, or you might have two different things, one that's a router and one's a modem. But sorry, or sort of, so you probably use a router, but yeah. And so we call that the gateway. So it's it's the last thing that belongs to you before you hand it over to Videotron. Okay? And then it will go to the modem. Okay? And then it's going to go through any number of computers that are part of Videotron's domain. Okay? So Videotron will have a bunch of computers that they run. It might go through 5 servers or 10 servers or something like that. Okay, so I'll denote this as Videotron. Okay, so that's good. All right, now Concordia kind of works the same way in reverse. Okay, so Concordia's website has a server, and Concordia have a bunch of computers that could do any sort of things like traffic inspection, load balancing, all sorts of stuff, intrusion detection. Okay, so they'll have a bunch of services that they're running, and there'll be an entry point into their network, which we'll call a gateway. And Concordia themselves will have an ISP. Okay, they might be their own ISP if they're big enough. But they, in this case, they don't. So they sort of have someone else that looks after it. Okay. And that organization is going to basically run everything between sort of, so you have kind of the internet here. I'll talk about that in a second. But once it enters into close to Concordia, it's going to fall under the domain of something else. Okay. So for Concordia, that thing is called RISC. It's a Quebec government thing for different universities and things like that. And they run a bunch of infrastructure. Okay, these things, Videotron and RISC, we give them a name. So we call them an AS for Authority Service. Is that right? Sorry, Autonomous System. Totally messed that up. Sorry, Videotron is Alice's ISP. Yeah. So Videotron is an ISP, and RISC is an ISP. But from a networking perspective, what we call these clusters of things that are controlled by someone is we call them an autonomous system. So it's just a term that the networking protocols use. So this is an autonomous system, and this is an autonomous system. Okay, and somehow in the middle, we need a final sort of connection where Videotron's AS talks to RISC's AS. Okay, so somehow the packet has to get from Videotron's domain to RISC's domain. Okay, Videotron knows where it's going based on the IP address, but it has to sort of cross domains here, okay? So there's going to be more or less 3 protocols that we care about that are going to be for each section of this graph, okay? When we're sort of talking locally, and we're trying to figure out how do I route things just amongst the routers that are in my house, I have a protocol, I call it ARP, A-R-P. Okay, thank you. Address Resolution Protocol, okay? And similarly here on the Concordia side, you'll have ARP, okay? When I'm inside of Videotron or I'm inside RISC, they have their own protocol. It's usually like hardwired. So they spend a lot of time configuring their routers. So their routers know exactly which routers to talk to. They don't try to discover other routers. It's all just hard-coded. Okay. And this is called IRG. Let me see. I wrote it down. IGP.
Internet Gateway Protocol.
It's interior gateway protocol. Okay. And then the final piece is how do you get from one, like how does Videotron find RISC and back and forth, okay? How do you make that big leap between AS? So in this case, we call it border, yeah.
These are transport layer, or what layer is that?
It's below transport.
It's not network?
It probably is network. It's been so long since I looked at the OSI model. I guess it's something I should know for this course. But yeah, it would be at the networking level because it's just about IP addresses and MACs. So it's somewhere between MACs and IP addresses. So ARP does some MAC-based stuff, and then this stuff is based on IP addresses. Okay. All right, so you have ARP, you have IGP, you have BGP, IGP, and then you go back to ARP, okay? And what I can do is if I want to get in the middle, I can try to attack more or less any one of these protocols, okay? And I may have more or less success depending on which part that I try to attack, okay? So let's go back to being in the middle. Okay, so first off, there's sort of 2 types of attacks that we can think about. We can think of a physical attack, and then we can think of like a network-based attack, okay? So physical attack would be like I'm literally touching one of these wires somehow, okay? So that wire is like going through the room in the ceiling, and somehow I'm able to tap it or something like that, okay? So you could tap a wire. Any of these like little computers or routers, you could try and infiltrate. So if I can get malware on one of these routers, then I can probably program it to either directly inspect traffic or send it somewhere where I can inspect it, and then I'll send it back, and then it will go on its way. Okay, so I can infiltrate the hardware. Another attack that's hard to put sort of in this diagram, but what I could do is I could set up a fake Wi-Fi router that has the same name as, say, Concordia University, called an SSID. So we call this an evil twin attack.
There's also like a ARP spoofing, right?
Yeah, so we'll get to that in a sec. Yeah. So I just make a Wi-Fi router that looks the same. I trick you, you connect to my Wi-Fi router instead, and now I'm in the middle of your traffic. Okay, so these are things that I can do with sort of physical proximity. The other way I can attack is by trying to get on the network. So if I can get on the network here, I'm not in the middle necessarily, so I'm maybe a peer of you on the network, but maybe I can get all the traffic routed through me by being on the same network. Okay, so that's where ARP spoofing comes in. Actually, we'll just call it spoofing in general. Network attack. So I join the network. And then I spoof. Spoofing just means I pretend to be. Okay, so I spoof being someone that's upstream from Alice. Okay, so I spoof an upstream node, I'll just call it, from Alice. So now Alice thinks that I'm on the path between her and Concordia, and so all the traffic is now flowing through me. Okay, how do I do this? Well, it depends if I'm at the ARP, IGP, or BGP level. Okay, so for ARP, I could use ARP spoofing. So that would be one way of doing it, the most common way. There are other ways, but that's the most common one. If I'm at the IGP level, I probably can't do anything. Okay, first off, I probably can't even become a peer on this network because it's Videotron controlled, unless if I have physical access. So infiltrate the hardware, I'll also note what we call an insider attack. So that's like someone who actually works at Videotron. Or a government that goes to Videotron and says, I have a warrant. I want to, put something on one of your devices so I can read all the traffic that goes across it.
That you build with the Canadian government, would they be able to do that? Without a warrant?
Definitely not without a warrant.
No, I heard even without a warrant.
So there is, it's a big complicated thing. So there are warrantless searches. It's controversial. You hear about it more in the US context with NSA doing it. Generally, the rule is you could do it if you're spying on foreign nationals, but you can't do it to spy on, like the Canadian agency couldn't do it to spy on Canadians. Yeah. But then nothing really stops the Canadians from spying on Americans, Americans spying on Canadians, and then them swapping information. So that's sort of the loophole. And so you have this sort of Five Eyes network of, yeah. So anyways, that's a whole other thing.
UK, Canada, Australia, New Zealand, and
So
US.
it's US. I don't know if New Zealand is one.
New
Is it? Okay. It could be, yeah. Okay, so anyway, so you have the infiltrate. So you can do ARP spoofing. IGP, you're going to have a hard time, but technically you could, if you could get yourself in there, you might be able to spoof. And then BGP, you can also spoof, believe it or not. This would seem the hardest because it's between these like big organizations of ASs, but you can do something called BGP hijacking. And this is the one I want to talk about today, okay? So I'll show you this, and then if you think about it kind of on a smaller scale, it's kind of the same principle as how you would do ARP spoofing and spoofing at other levels of the network itself.
then you can do that using software?
Sorry, say it again. So the
Because ARP spoofing on Kali Linux, they have a tool called BetterCap that can do it, and it's really easy.
Mhm.
But is there also like software tools to do it?
yes, I believe there are. Yeah, so I think like different software will do it. The hardest part is getting yourself close enough to be able to do it. But once you're close enough, I'm sure you can do it pretty easily. Yeah.
As an attacker, what would be the best attack? I'm guessing fluid attack?
So it depends. So it's a good question. So what's the best attack? It depends sort of on your target and what you have access to. So if I'm attacking you and we're both on Concordia's Wi-Fi, I'm going to try and do some ARP spoofing to get you going through me. That would be my best attack. Or the evil twin would be the best. Yeah. If I'm in one country and I'm trying to infiltrate traffic for a totally different country, right? Then this kind of stuff isn't going to help because I'm not on the local network. I'm going to have to do BGP hijacking.
But ARP spoofing can be detected because you're changing the MAC address of the router to be your own MAC address, right?
Yeah. So
So addresses that are the same.
Yep, so there are both attacks and mitigations at this point. And ARP spoofing is like a very old attack. It goes back. And so there are defenses against it as well. Yeah. So I'm not saying it just universally works on every network. But yeah. Okay, so let's think of the BGP case. Okay, so the first thing I want to do is I want to talk a little bit about IP addresses themselves. Okay, and in specifically what we do is we sometimes call something an IP address prefix, and so I'm going to define what that means. Okay, so an IP address prefix looks like an IP address. Except for it has an extra thing at the end. Okay, so we'll have a number. The number will be 16, so it's going to be some number between 0 and 32. And each one of these digits is between 0 and 255. Okay, so that's the same for each one of these digits. Okay, so you have 4 numbers. Yeah.
Sir, why is it between 0 and 32? Because that's 2 bits.
Yes, exactly. Yeah. Yeah. So you need 32 bits to represent this, to represent all 4 of them. Yeah.
We call that cider notation.
Sorry, you call?
We call that type of notation with the / cider notation.
Perhaps. Yeah. Yeah. Okay. All right. So this is what it looks like. We have a slash. Now, what does this actually mean? Okay. What this means is that the first 16 bits are fixed. So whatever this IP address says the first 16 bits are, that's what they are. And the rest of it is like a wild card. It can be anything you want. Okay? So if I see this exact IP address with 16, what that means is that the 132 is fixed, the 205 is fixed, but the last 2 bits are not fixed. Okay? So they can be literally anything
From 0 to 255.
from 0 to 255 for both of them, and it will match that prefix. Okay? So as long as it starts with 132.205, it's going to match this prefix regardless of what this thing is. Okay? And so what routers will do is they don't want to say, here's all the IP addresses I own. It's too much to say. Okay, there's too many IP addresses to say. So what they like to do is give a range. They say, I control everything from this to this. Okay, and so that's all a prefix does, is it's just a way of specifying a range of IP addresses or a block of IP addresses that you control. Okay, so what that means is if I say I control this, it means I control every IP address that starts with 132.205. Okay, now there is someone in the world that literally does that. Okay, and that someone is RISC and Concordia. Okay, so this is a block of IP addresses that Concordia owns, and so they might own other IP addresses, but every IP address that has this pattern is something that's owned by Concordia. Okay, and when Concordia advertises it to the world and says, send your internet traffic to us, they're going to use RISC as the organization just to advertise it. Okay, so they're going to tell RISC, send anything that looks like 132.205, send that our way. Okay, and then once it hits us, then we'll figure out how to route it internally using our own internal routing protocols, and we'll make sure it gets to the right computer in our network. Okay. Now, there's another concept that I want to define, which is, well, let me just give an example. So consider a different prefix. 132.205. Say 244.0/24. Okay, so what does this prefix mean? Okay,
The last number is from 0 to
We can
55.
yeah,
play along with the last 8 bits.
exactly. So the
These are fixed.
these are fixed, and 32 minus 8 is 24. Yeah, so this all of these are like a wild card. Okay, so you can play around with these 8 bits and it will still match this prefix. Okay, so let me call this prefix A, and I'll call this prefix B. Okay, and some terminology that we use is we say that B is more specific than A. Okay, so it's more precise. It gets you closer to the computer that you want. Okay, so if you're trying to route information and people are telling you A and people are telling you B, you'd rather just send your traffic to B because it's going to be a little bit closer to the information. Okay, this is how BGP works. Okay, so if there's more than one route that you can take, it will take the route that's the most specific. Okay, and this is exactly what an attacker is going to exploit. It's actually a very simple attack at the end of the day. Basically, the attacker is going to go and they're going to say, I want all of Concordia's traffic to come to me. What they'll do is they'll say, hey, I accept Concordia's traffic. And what they're going to do is they're just going to announce a prefix that's a little more specific, maybe 1 bit more specific than Concordia's. Okay, and then everyone's going to say, okay, I could send it where I've always been sending it, but now there's this new route. It's a little more specific, so I'm going to send it there instead. Now all of a sudden, all of Concordia's traffic comes to me, all right, and I'm in the middle. I can do whatever I want. Then I can route it properly to Concordia, or I could also just drop it. So you see this also in denial of service attacks, where you get the traffic routed to you, you just drop it. It's called a black hole, and then the traffic disappears. Okay, this happens all the time. Not all the time, but it's happened sometimes in the context of attacks, and sometimes it happens by accident. So someone mistypes something, and then they end up accidentally. So there's an example where someone got all of YouTube's traffic flowing through them by accident, and then yeah.
You use this on like a local network from a house or something like that has like maybe 5 devices that are there. You're gonna be able to get the traffic from all those devices?
Yeah, so this protocol,
Yeah, go ahead.
so I mentioned that these are called ASs, autonomous systems.
Yeah.
Okay, I'm going to give you some details, but ASs have to be registered.
Okay.
So there's an internet kind of authority, and they give ASs and they give them a number. So if you're not an AS, you can't do this attack,
Oh,
essentially.
it only works for AS.
Like single AS number that is unique. No two ISP has the same AS number. It should be completely single.
Yes, correct. Yeah,
Then
yeah.
an AS would have more ways to detect these type of things if it's like something registered by a body, right? If it's,
Yeah.
I imagine a school or a bank or something like that has like mechanisms to see if somebody's trying to like.
Yeah, so whether they monitor it or stop it, that's a different scenario. All they do is they sit back, and it's not even a personal thing. It's just you log in. Like, I own a bunch of IP addresses. That's registered to me by someone, and they give me a website. And so I just type in the website, I want to use ASN, blah, blah, blah. And now that's my ASN. And so that's the only interaction that we have, essentially. Yeah. So later I'll, anyways, I don't want to get too far ahead of myself. Okay. Also, just while we're here, usually the smallest number in the range we call a network address. So if we fill the wildcard in with all zeros, usually sysadmins will set that aside. They won't assign it to a machine, and they'll just say we're talking about the network as a whole. And then the highest address in the block, if you fill it all in with, say, 255s, that's considered a broadcast address. So if you send information to that address, then the network will actually relay it to all the nodes on the network, all the IP addresses. Okay, so the high and the lowest usually tend to be reserved for those purposes. They don't have to be. There's nothing in the protocol that says you have to do it that way. It's just convention. And then everything in between might be assigned a host name. So that's why, like, usually your router will be blah, 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 .0.1, not 0.0. Usually it's a local network thing, but anyways, okay. Okay, so basically BGP, what you do is you become an AS. Okay, so you then what you do is you talk to the other ASs and you say, okay, what are the routes that you take care of? What's your prefix? Okay, so the ASs will exchange prefixes. How do they exchange it? Well, normally you're connected directly to some ASs. Okay, so let's say we'll do Videotron. It will have a direct connection to a bunch of people, like think Canada, Montreal, like kinds of organizations. Okay, and then let's say it wants to reach Google. It might not have a direct connection to Google, but it will ask somebody who will provide Google to them. Okay, so there's usually like a service here that's like your upstream provider, and it kind of connects you to the rest of the internet. So it's kind of like all the other ASs on the internet. And then Videotron will have boxes that are sitting around Montreal. And other people like RISC, for example, will be co-located in those boxes. And so they'll actually have a direct connection to RISC and to other, like sort of maybe Bell, that type of thing. Okay, so sometimes they can go directly to the AS they want. Sometimes they'll ask a provider, and then they usually pay for this, and then the provider will figure out all the other ASs on their behalf. Okay, so Videotron.
What was the risk again?
What are which? Sorry. So RISC is Concordia's Quebec government thing. Yeah.
It's only for universities?
Yeah, exactly. Or education anyway. It might be high schools and SAGEPs. But. Okay, so Videotron, their actual ASN, their AS number, is AS5769. And then RISC has ASN AS550, which is a very low number, and they're actually an old thing. Like when you look it up, I think they started in 1978 or something like that. So they've been around a long time. Okay, if you want to see information, if you're curious about this thing, there's a good website called PeeringDB. And so you can type in things like, let's try AS550. And okay, why didn't that work? I'll just put in RISC and see. Okay, so here's RISC. Maybe I wrote the number down wrong. It says actually the number is 376, so I perhaps wrote it down wrong. So let me change the notes. Okay, and so you can see some information about them. And then you can see that they have some facilities around Montreal. So one of the biggest facilities in Montreal is this one called Montreal 3. And inside of Montreal 3, you have tons and tons of other providers who have computers here, okay? So one of them, for example, is Videotron. So let's see. So Videotron is here. You can see that they are AS 5769. 5769, so I got that one right. Okay. And so that what that means is that it's not strictly necessary because they're co-located, but usually if they're co-located, they're going to have a direct connection to each other. They still have to sort of manually set that up. So these are two ASs. There's literally a place in Montreal you can go to. I've never set foot in Montreal 3. However, I have gone to Montreal 11. Let's see if I can pull up. And this is a very cool place. It's like, it's hard to describe. I forget what street it's on, but it's kind of like there's a mall and there's sort of like an overpass. So it's sort of like a tunnel, but it's only like about a block long. And you walk down, actually the address is here, so you can see it. And so you, I'll just show you for fun. So, okay, maybe this isn't the right facility. Yeah, so this is the one, I think. It's not the right one either. Okay, I'll try one more, and if it's not right, I'll just tell you from memory. So it's definitely not that. Let me try this
Is
again.
it like a data center?
Yeah, so it's like a data center. So I think I just typed in the address wrong. Hold on. Why is this not? Oh, it is. Anyways, so it's sort of like a nondescript. Basically, you're in this overpass and you're walking along, and there's this door, right? You can't see through it. There's like 3 security cameras, and that's it. There's just a door, and then if you move over a bit, you see these like sort of grills where there's fans because it's like circulating the air. Anyways, if you go into the building, this is where all the oversea fiber optics come into Montreal. And it serves up more or less all of North America. So the fiber optics, they sort of stop in, I think it's Newfoundland or maybe PEI or somewhere out on the east coast of Canada, but they just repeat it. So all they do is the signal's weak, so they attenuate it, or sorry, they do the opposite, they boost it, and then they send it onto Montreal. But Montreal does all the processing. So where the fiber optics turn into networking happens basically in this building. And so you can walk around, and then there's some like top secret rooms too that you're not allowed to go in because it's like government controlled things. And so anyways, it's very interesting. Maybe I can get a tour of there as a field trip for this class, but probably not. But anyways, okay, so Videotron and RISC, they're probably sitting in the same facility, or they are sitting in one of these facilities, and so they're going to have a direct connection to each other, and so they don't have to go upstream. Okay, they're going to know each other's prefixes, and so they're going to be able to send messages back and forth. Okay, now what's the actual attack itself? So there's different ways that you can try and hijack BGP. The simplest way is, first off, you have to be an AS. So you can't just do this from your house using your normal computer. How do you become an AS? So there's different ways. So you could just rent one, maybe. You could borrow one. You could try to infiltrate one with malware. get physical access to one. You could also try to just spoof being one. So you might not actually be one, but you might just start announcing things as if you are, and then rely on maybe like an implementation not working correctly or something like that. And so people aren't throwing away. And if you can get one AS not to throw it away, what the ASs will do is they'll gossip to each other and they'll tell each other about you. Okay, so if I can trick one AS into thinking I'm an AS even though I'm not, then it will repeat what I told it to the rest of the people it knows and it'll eventually get around the network. Okay, so these are things that you could do. Okay, the next thing you'll do is you're going to announce IP prefix for basically who you want to man in the middle. Okay, so for the man in the middle target. Now, you're immediately going to compete with the real person. So let's say I'm man in the middle in Concordia. Risk is also announcing that they control the same prefix. And so I'm immediately going to compete with them. Okay? So I'm going to be competing. Yeah, so I'm going to compete with the target's AS. And now it's going to be a question of what's the tiebreaker. Okay, so other ASs are going to see two of these things. They have two routes. What are they going to do to break the tie? So generally, it's very complicated. So they have a long list of criteria. And some of the criteria is like, how long have I known you and how long have you been sending, have I been sending stuff to you? And has there ever been problems in the past? And there's no way I'm going to beat that. If I'm a new entry and they've never heard of me, they're never going to prefer me, okay? So basically, I'm going to lose at every tiebreaker with one exception. And that exception is if I offer a more specific prefix, then they're going to prefer me all of a sudden because my prefix is more specific. So it's not a tie anymore. I'm winning based on that, okay? So the basic way I do it is I offer a more specific prefix. Okay, and then I sort of win. Okay, if I offer the same prefix, if I offer a less specific prefix, I lose by the same rule. And if I offer the same prefix, I probably am going to lose. Yeah. So just based on priority rules. And we don't have to understand what all these rules are. Okay, so for example, let's say that risk is announcing 132.205.0.0/16. Then what the adversary will do is they'll announce, say, 132.205.0.0/17. Okay. Now, technically, this is only getting the first half of these addresses. Okay, because I'm saying that there's a 0 in the 17th bit here. Okay. So if I care about, I can't attack all of Concordia at once. But if I care about IPs in the first half of this range, then I could announce that. If I want them in the second half of their range, then I could announce, for example, 132.205.0.128, which is halfway between 0 and 255. And that will give me the second half of that range. Okay, so that's fine. Sorry, that should be 128.0. Okay, now this attack isn't quite as easy as I make it sound, but it is something that you can do. And as I mentioned, it's happened in real life before. So like one big incident happened in 2008. This was an accident. So Pakistan Telecom. Announced a /24 prefix for YouTube. Okay. Well, YouTube's AS was announcing a /22. Okay. So what happened? Basically, all the traffic going to YouTube, not all of it, but like a lot of it, a lot of that is now going into Pakistan to their telecom system, which cannot handle that amount of traffic. And so it just disappears. YouTube basically goes offline for a lot of the world. If you were outside of this range, like, so because it's more specific, you're also getting a smaller set of IP addresses. So there were some people who could still connect directly to it, but for most of the world, there was an outage, okay? And there's no way to fix it. Everyone sees it, they see what happens. They can kind of revoke the announcement, but it's going to take a couple days for everyone to update their tables. And so what Google did is they said, okay, we got to fix this. So what they did is they started announcing /25s. And so they kind of broke their domain up into a whole bunch of these 25s. And then now all of a sudden everyone switched back to Google because now Google is like the more specific prefix. And
Somebody from Pakistan who did that?
sorry?
There was somebody from Pakistan who did that?
Yeah, presumably. And it was purely accidental. So they, I can't remember why they did it. I think they controlled like a similar IP range or something, and something got messed up. But yeah. Actually, I kind of remember now. I think they were actually trying to surveil on YouTube. So they were trying to get some stuff sent through them, but then they messed up somehow, and they ended up sending all the traffic through. Yeah. So, or they were trying to do something. I don't know. But anyways, it was accidental, but not necessarily like just a pure accident.
And they had the same prefix.
So I don't actually, I think they were actually trying to shape YouTube's traffic within the country, but they didn't mean for it to go outside of the country or something like that. I'll have to look the story up again. I forget what it was exactly. So it wasn't an accident in the sense that they mixed their IP address up with YouTube's. They were trying to do something with YouTube, but they weren't trying to infect all of BGP with it. Yeah. Okay, and then last year, so this is an old attack, but this problem is still around. So you can find more recent examples of Verizon, Cloudflare in the last 2 years where this type of stuff has happened. Okay, so it's not a fixed protocol. It's still something that is going on. Okay, there is a way of solving it that's been proposed, and it's sort of rolled out in part, and that's we can use our friends' digital signatures. Okay, so we saw cryptography, and what we could do is we could stop, say, Pakistan Telecom from announcing IP prefixes that belong to Google by basically saying, well, whoever owns those IP addresses has to sign it. So I'm not going to believe any announcement unless if it's signed by the party that owns it. But in order to sort of do this, I need three things. One thing is I do need keys for everyone. Okay, so I have to know what everyone's keys are. Secondly, I have to know who owns what IP address. Okay, so I have to know who that belongs to. And then the third thing is I need an actual protocol for creating these signed messages and sending them around and verifying them. So there is some solutions to all of that. Yeah. Okay. But anyways, we only have 5 minutes left, so I don't want to get into that whole protocol. So I'll show it to you quickly next class, and then we'll go back to now that hopefully you believe that you can kind of get in the middle. By the way, ARP spoofing, it's a little bit different, But all of these have the same flavor, which is there's not a single party that knows everything. There's not like an authority for the internet. And it's like, I want to route to this person. I'll go ask the authority, and the authority is going to tell me. Okay? All of them have the flavor of there's no one really in control. They're all kind of decentralized. And so they're all figuring it out themselves. You have a bunch of people, no one's like leading the system. And so they're all trying to discover paths just by asking, friends, and friends tell them different information. And so in that kind of system, it's a lot easier to inject yourself, spread false information, and have people believe it because there's no authority that's disputing it. Okay, that's not to say that I like centralized systems with authority. I work a lot on decentralized systems like blockchains and things like that. But it's just a known trade-off. So if nobody's in control, then you have to deal with these sort of attacks of it's hard to say like who's authoritative over things. Any questions?
I have to look more into this.
Yeah.
When you were showing the example of like risk announcing a prefix and the adversary announcing similar prefix, why did the adversary have the 17 and what does that mean?
Okay. Yeah. So the
Specific.
All the way down.
yeah. Before we go there, I'll just show you this. So where was it? Yeah. So if we compare A and B to each other, we had this idea that B is more specific than A, meaning it controls a smaller number of IP addresses. And in order to be more specific, if you just want to look at it with your eyes, just look at the slash part. If that number is bigger, then it's more specific. So a /17 is bigger than a /16, etc. Yeah. So then if we go down here, risk is announcing a /16. So a /17 is more specific. And so it could be a /18, a /20. It doesn't matter. Like anything that's more specific than /16 is acceptable. But yeah.
The more specific bit is in the 0.
Yeah. So you start at the front.
Stage 8, and there's one more, right?
Yeah, that's my question. Like, where's the one more that is fixed?
So the one more is the first bit of these. Let me just draw it out. Okay, so this thing, let's just unpack it. So in terms of bits, it's, what did we say? It's 8 bits long. So this would be 0, 0, 0, 0, 0, 0, 0, 0. Yeah. And so 16 will cover this, and it won't cover any of this. 17 will cover this, and it will also cover the first bit here. Yeah. So this stuff can go from 0 to 1, 1, 1, 1, 1, but that leading 0 has to be there. Does that make sense? Yeah. I didn't explain that very well, so thanks for the question. Yeah. Okay, other questions? Yeah.
I don't know if you have time, but why don't, like in a handshake where destination is known, why don't we have like trusted, it's like in a centralized and decentralized systems that you spoke about. Like why don't we have a trusted button like, okay, the prefix is, for example, this, like I won't go, this guy won't go for like a Pakistani, if he's like in US or for example, like he wants to go to YouTube for example.
Yeah.
Like it's about trust.
Right.
Like why isn't that like in that way and not like it's like a free market?
Yeah. So there's two answers to it, 3 maybe. So historically, we didn't have. Oh yeah. Okay. So the question is basically, why don't we introduce a trusted intermediary that can introduce things? And if there's something completely unreasonable, like traffic destined for the U.S. is going somewhere else, they could at least intervene in those cases, right? And say. So historically, we didn't have such a party. So that's the first reason. The second reason is it's a lot easier to say, like, that looks weird because you're thinking like a human, but these are just machines. They're just looking at numbers. And so they don't have that notion of, oh, this is US traffic or this is going to Pakistan now. Like, that's weird to us. right? Because we know what those countries mean and things like that. Like they're just computers, they're just looking at numbers, yeah? And then the third thing is we are now introducing that. So when we introduce this idea of signatures, we're not going to introduce exactly that, but we're going to have to introduce who's authoritative over which prefixes in order to sign it. And so there is a party that's going to play more or less that role that we'll see next class. Yeah. Okay, other questions? Okay, great. I'll see you all next week.